So let me just come back now to the syllabus and illustrate with 1 or 2 slides the kinds of things we're going to be doing throughout the course. So with respect to the tectonic stress field, we have to recognize that geologic processes are responsible for the stress field. And it was recognized in the 1930s by a British geologist by the name of E.M. Anderson that in general you could classify the forces, the stress field in the Earth, into 3 major categories. He called one category normal faulting. Of course, the second category, a more compressive stress state, is strike-slip faulting, and the most compressive stress state is reverse faulting. And what E.M. Anderson did, and his real insight, was to recognize that the relative magnitudes of these 3 principal stresses are changing in each of these stress fields. And the way to keep track of all this is to keep your eye on the vertical stress. In a normal faulting domain, the vertical stress is the largest of the 3 principal stresses. And if faulting is going to occur, it's going to be an extensional fault, a normal fault, which strikes in the direction of the maximum horizontal stress, and the slip on that fault is in the opposite direction, in the direction of the minimum horizontal stress. And he called this normal faulting because he was studying coal mines in the UK, and when the mine would normally hit a fault, they would find the coal on the other side, below them, and that would be a normal fault where what's called the hanging wall moves down with respect to the footwall of the fault. So in a normal faulting stress state, the vertical stress is the maximum stress, the maximum horizontal stress is the intermediate stress, and the minimum horizontal stress is the least principal stress. By the way, in this class, we will use the convention that compression is positive. A compressive force is a positive force. Now that is the standard convention in structural geology. It's the standard convention in rock mechanics. It is not the standard convention in material science. And when our colleagues in material science are studying the failure of materials, failure is much more prevalent and prominent when the materials are in extension. So our friends over in engineering use extension as being a positive stress because that's what's important to them, but what's important to us is the fact that compression is a positive stress, and the stresses in the earth are always compressive. In fact, the stresses in the earth are always such that the minimum stress, in this case the minimum horizontal stress, is greater than the pore pressure. Okay, now the pore pressure in an open system, as we'll see, is just the weight of the water above a depth of interest. And the least principal stress always has to be greater than the pore pressure, or the earth will sort of self-hydrofrack, okay? Because the tensile strength of rocks are very low, something we'll discuss in chapter 4, okay? So the stresses are always compressive, the stresses are always positive, and the stresses are always greater than the pore pressure. Now, the next most compressive stress regime is strike-slip faulting. Now, instead of the vertical stress being maximum, the vertical stress is the intermediate stress. The maximum horizontal stress is greater than the vertical stress, which is greater than the minimum horizontal stress. If faulting occurs, strike-slip faults are expected to be vertical and oriented about 30 degrees from the direction of maximum horizontal stress. We'll derive that. You'll see where that number comes from. The most compressive stress state is where both horizontal stresses are greater than the vertical stress. This is called reverse faulting. If faults are active, those faults are dipping at about 30 degrees. They dip in the direction of the maximum horizontal stress, and if you're a miner standing on that fault, the hanging wall, the rocks above you, are moving up with respect to those in the footwall. Okay, so we have to, as we begin to study the stress field, we're going to first try to understand the vertical stress, which is of relevance for the depth we're interested in, and then we're going to try to understand the relative magnitudes of SH max and SH min with respect to the vertical stress. Are they both smaller than the vertical stress? Are they both greater than the vertical stress? Is one greater and one less? And this is not an abstract concept. As we look at the central and eastern United States, an area that's currently being developed in many states for horizontal drilling and shale gas and tight oil development, what we can demonstrate through looking at earthquake focal plane mechanisms, and in Chapter 5 we'll talk about what earthquake focal plane mechanisms are and what they teach us about stress, we can actually characterize the relative stress magnitudes. And this is from a recent paper by a former PhD student Owen Hurd and I. And what we're doing is using color to simply illustrate how relative stress magnitudes change from, say, central Texas all the way to the northeastern United States and southeastern Canada. And the dark blue color means that the two horizontal stresses are very low with respect to the vertical stress, and the dark red color indicates that the two horizontal stresses are in excess of the vertical stress. And so we go from sort of a normal faulting regime to a strike-slip faulting regime to a reverse faulting regime as a result of normal geologic processes, okay? And if one were to assume that the stress state were the same in New England as it was in Oklahoma, you'd be dead wrong. And so we have to build this stress model. We have to understand what the stresses are. And of course, once you're in a more restricted area, the variation might be relatively minor. But as we think about stress in the earth and how it affects various processes, we have to understand where we are, what the current geologic processes are in the area. But in fact, we don't have to look at this as an academic exercise. We will actually let the data coming from the wells inform us about what the stresses are. So if you think about the vertical stress being the maximum stress, as it is in the diagram on the left, and the two horizontal stresses being lower, and we have the pore pressure shown by the dotted line, you can make some very crude estimates of what stress magnitudes are. Okay, the vertical stress goes up in sedimentary basins at about 23 megapascals per kilometer. That's for a density of rock about 2.3, which is a normal sedimentary rock with something like 15% porosity. That corresponds to 1 psi per foot in English units, and we'll kind of go back and forth between international units and English units. 23 megapascals per kilometer, 1 psi per foot is a typical overburn value. If pore pressure is hydrostatic, the pore pressure is going up by 10 megapascals per kilometer, or about 0.44 psi per foot. And in a normal faulting regime, the vertical stress, the pore pressure, and then we have the minimum horizontal stress and the maximum horizontal stress intermediate between the two, defining the stress state. If we are in a strike-slip faulting regime, then the minimum horizontal stress is less than the vertical stress, and the maximum horizontal stress is greater than the vertical stress. And if we're in a reverse faulting regime, both horizontal stresses can be larger. In fact, there's not enough room on the graph. Both horizontal stresses can actually be quite large, and we'll talk about that later. And well, I'll build on this concept here with respect to some issues we discuss in Chapter 4 in a minute. So just knowing something about the relative stress state begins to give us a sense of what the stress magnitudes are. We know very little at this point. We know it's a normal faulting regime, and yet suddenly we know that, at a depth of, well, let's take 3,000 meters or 10,000 feet, we know that the overburden is, 3 times 23, that's 69 megapascals, or about 10,000 psi, and the two horizontal stresses are less than that, and the mean stress is, something like maybe 7,000 or 8,000 psi, 50, 60 megapascals. At the same depth, in a compressive regime, the vertical stress, the question is whether or not the relative stress magnitudes change as a function of depth. And in general, they don't, but we have seen instances in which they do. The point of this is to integrate these concepts over many different depths. But in general, you're going to be interested in a limited range of depths also, and you want to be able to characterize the relative stresses at those depths. Where this is of most concern is when we're using earthquakes to kind of inform us about the relative stress state, because often reservoirs are at depths of 2, 3, 4 kilometers, and the earthquakes might be at 5 or 10 kilometers. So when we're using earthquakes as an indication for relative stress magnitudes, we have to pay very, very close attention to that question. Okay, so as I was saying, at a depth of about 3,000 meters or 10,000 feet, the stresses the mean stresses in a normal faulting regime are very much lower than the mean stresses in a reverse faulting regime. Okay? All right, pore pressure. Pore pressure seems like an easy thing. You go down in the earth, and the pore pressure in the cracks and pores of the rock represent the weight of the water, that's the fluids that are above us, just like kind of going down in the ocean in a submarine. Well, that's often the case, and it's often not the case. And here's a case we'll talk about. In this case, hydrostatic pore pressure. Hydrostatic pore pressure is shown by this line. That's 10 megapascals per kilometer, or 0.44 psi per foot. And what you can see is that the pore pressure is quite a bit higher at shallow depth. The pore pressure is hydrostatic, and then the pore pressure is building up as we get deeper. And in fact, in some cases, they're actually even losing circulation because the mud weight is not only higher than the pore pressure, but it's higher than the least principal stress. And you can see that the pore pressure as it goes up is discontinuous with respect to different reservoirs, which are separated by different shale units. So we can go from cases in which the pore pressure is 10 megapascals per kilometer, 0.44 psi per foot, it's hydrostatic, very simple, easy to understand, to cases in which it's very complicated, and first we need to understand it, and second we need to be able to predict it, and we need to be able to work with the pore pressure in a quantitative way. When the pore pressure is elevated at depth, which is shown schematically here, we see near hydrostatic pore pressure at shallow depth for our normal strike slip and reverse faulting cases, and near lithostatic pore pressure. The pore pressure is getting up. As the pore pressure goes up and becomes close to the overburden, what you see is, because the least principal stress has to be greater than the pore pressure. In a normal faulting regime, the maximum horizontal stress is greater than the minimum horizontal stress, and the vertical stress is the maximum. Look what happens. We have almost an isotropic stress state. Okay? It's still normal faulting. Vertical stress is still largest. The minimum stress is still bigger than the pore pressure, but there's very small differences between the three principal stresses. Remember I said how different normal faulting and reverse faulting were when I showed the hydrostatic pressure version of this same slide. Now, when we look at it, we see a near hydrostatic stress state here, a near isotropic stress state in both cases. So as pore pressure gets elevated, the stress field becomes more uniform. The basic principles are the same. SH max is still greater than SH min, which is still greater than SV, But at very elevated pore pressures, as we'll see in chapter 4, the frictional strength of the crust is so low that it can't sustain big stress differences. And so the difference between normal faulting and reverse faulting, which is just huge from a stress magnitude perspective at great depth when we compare normal faulting and reverse faulting, when pore pressures are severely overpressured, when pore pressure is very, very high, that difference sort of disappears. In fact, when we start talking about the wellbore stability problem, wellbore stability means getting the stress right and getting the rock strength right in a hydrostatic pressure regime, because the stress differences can be quite large. If you're drilling in an overpressured area, wellbore stability kind of means estimating the pore pressure right and getting that mud weight, excuse me, to fit in that mud window, okay? So it's really a very different environment. And so stress and pressure are very closely coupled.